And I should be live. Am I live? That's good news to me. Why is there air? Why do we have air? Where did it come from? What's it made of? Who knows what it's made of?
Mostly oxygen and nitrogen.
Nitrogen and oxygen, almost entirely nitrogen and oxygen. It's about 3/4 nitrogen, 1/4 oxygen. The actual oxygen percentage is about 21%. There's a little bit of carbon dioxide, about 300 parts per million and growing. There's tiny bits of other gases, but for the most part, it's nitrogen and oxygen. Where did the nitrogen come from? How do we have nitrogen, free nitrogen, in our atmosphere? Where did that come from? It probably came from ammonia, which is fairly common in the universe at large, especially in molecular clouds, and that probably got ripped apart by sunlight. Where did the oxygen come from? Plants, green plants. Green plants do this. They emit oxygen. And it's a good thing they do because we use that oxygen. The plants use sunlight to gather energy. And the way they store that energy is they tear the oxygen off of carbon. And they put all that energy into the carbon atom. They mix it with a few hydrogens to turn it into sugar. And then they take the sugars and they stack them end to end to turn it into wood. And that's why wood burns, by the way. Wood burns with solar energy. The oxygen ratio in our atmosphere is about 21%, but it was not always so. Before there were plants, there was no free oxygen. And in fact, free oxygen is something you don't expect to find in a planetary atmosphere because oxygen doesn't want to be free. Oxygen combines with things. For example, it combines with iron. If there were any iron anywhere on the surface of the planet or dissolved into the oceans, the oxygen would disappear overnight. It would rust that oxygen, it would rust that iron away. And in fact, that's what happened for the first 3 billion years of the history of life on Earth. Every oxygen atom emitted by a plant got grabbed by an iron atom and fell to the bottom of the sea. Because in those days, there was a lot of iron dissolved into the sea. And so this rust, iron oxide, fell like rain down to the bottom of the seafloor. Nowadays we call this iron ore. It took 3 billion years to get rid of all the iron in the oceans. So it was only about 1 billion years ago that oxygen began to accumulate in our atmosphere. And it accumulated and it accumulated and it accumulated. At one point, about 250 million years ago, the atmosphere was almost 50% free oxygen. In that kind of an atmosphere, you could sneeze and start a forest fire. The animals grew to enormous size, and I'm not talking about the dinosaurs here, I'm talking about dragonflies. There were dragonflies that had 6-foot wingspans because there was so much oxygen in the air, they had plenty of free energy. Eventually, that oxygen level tapered down a little bit, and nowadays we have a more rational amount of oxygen in the atmosphere. Although, frankly, living in a sea of oxygen is fraught with danger, which is why we all have smoke alarms in our houses. But of course, this is not what we're supposed to be talking about. The name of the talk I'm going to do today is called Functional Programming. What, where, when, why, how, or the failure of state. How many of you are functional programmers? Meaning that you program in some nominally functional language like F#? Who's doing F#? Is this a functional language? Who's doing Scala? A few of you. Who's doing some kind of Lispy language? Ooh, some Lispy languages over here. Who's doing a real functional language like Haskell? Nobody. Okay, how about ML? Yeah, nobody. Okay, so fine. I didn't name them all. That's all right. We're going to be talking about functional programming, not a functional programming language. At the end of this talk, I'll show you a little bit of Clojure, which is a Lispy kind of language. This guy's name is Rich Hickey. Who's heard of Rich Hickey? All right, this is the author of the Clojure language. He is a brilliant speaker. Find some of his talks on YouTube, and you will be amazed at what a good speaker he is and the interesting insights he can give you. One of his talks is about state identity and value. Briefly, one is a value. I don't think that's lost on anybody. The next line says that X is an identity, an identifier. And in this case, that identifier identifies the value 1. The next line, however, is problematic because it suddenly says that the identifier will identify a value, but you've got no idea what that value is. The identifier has a state, not a value, and that state can change. The subject of this talk is that state has failed, but how can this fail? A statement like this is so common in our programs, how can we call this a failure? Is that program stateless? Well, from the point of view of the program, it's stateless. It does have an effect. It seems to print something on the screen, but we can ignore that. From the point of view of the internals of this program, there's no state being changed anywhere. So here's an example of a program which does something nominally useful and does not change any state. Here's another program. And probably all of you have written this program at one time in your life. It is the squares of integers program. It prints out the squares of the first 20 integers. And what we notice here is a variable that changes state. Now, this looks perfectly normal. What's a for loop for? If you can't change state, right? A for loop changes the state of variables. This works just fine, but it is stateful. It is not stateless. And we're going to talk about why that can be dangerous. Now, can this program be written so that it is stateless? And it can. You could write it that way. It's not particularly useful, but no variable is changing state in here. There's a better way, of course. You could write it that way. This is a recursive algorithm. Print squares calls itself. If it's greater than 0, it continues to call itself. If n is greater than 0, it continues to call itself. And for every iteration, it prints out the square of that particular value of n. No variable changes state here. New variables are introduced. The variable n gets recreated and recreated and recreated, but at no point does any variable change its state. This is a functional program. Sort of, written in a non-functional language, but it is stateless. By the way, how many of you are Java programmers? Some of you. See, I got these big lights in my eyes so I can't see you, so get your hands way up in the air. Java programmers, yeah, there's some of you in here. How many of you are .NET programmers? Seems to be a slight bias in this audience. Java programmers, does your execution platform support recursion well? .NET programmers, does your platform support recursion well? Does it, for example, allow for tail call optimizations? It's an interesting question. The Java runtime does not. The .NET runtime does in some circumstances. A program like this, if you were to change this number to, say, 2 million, to print out the first 2 million squares, might cause the stack to blow. In fact, this particular function would cause the stack to blow because it's not tail call optimized. So the stack will blow here, whereas the original one that was stateful, wouldn't blow the stack on anything. So there's a certain memory usage here. Memory is getting used in an inefficient way if you cannot tail call optimize. By the way, what the heck is it with these platforms? .NET and Java. Why would tail call optimization even be an issue? The year is 2014. This is an optimization that was invented in the 1950s. What's up with our platform people? I think they were kids out of school. Who read this book? Some of you have read this book. All right, wonderful book. It's free, by the way. You can download it off the web. They give it away now, which I think is remarkable. Along with it, they give away all the video lectures of these two guys. You can watch them teach the computer science course at MIT in the 1980s as they deliver the content of this book. The book is fascinating. I picked it up and read it maybe 10 years ago. And I noticed something about this book right away. It makes no apologies. It moves at light speed. You open up the book, you start turning the pages, they hit concept after concept after concept. They don't diddle around, they don't over-explain, it just goes boom, 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 very fast. And as I was reading it, I was just throwing the pages. It was an exciting book to read, if you can think of a computer science book as being exciting. But I was excited by this book. I'm throwing the pages, reading it, oh, this is cool. The language inside was Scheme. They don't really explain Scheme, but it doesn't matter because Scheme has almost no syntax, so you can easily infer what these programs do. Page after page after page after page, they're talking about basic algorithms, queuing structures, stacking structures, symbol tables, message passing, all kinds of stuff, tons and tons of code. You get to page 249, I believe it is. And they stop. And they apologize for what's about to come. They say, we're sorry now. We're going to have to corrupt our currently very clean view of what a computer is. And they go on paragraph after paragraph apologizing for what's about to come. And they introduce an assignment statement. And I was thunderstruck. I stopped reading and I stared at this thing, and it made the claim that no assignment statement had been used in any of the previous code in the 249 pages I had read. I had to go back and read that code to look for an assignment statement, and nowhere in there was there an assignment statement. That really fascinated me. I thought, wow, they did that whole first 250 pages with no assignment. Typically, in a computer book, the first thing you learn is an assignment statement. They delayed it for 259 pages, and they apologized for it. I'll tell you why they apologized for it in a minute. Here's how their model of computing worked before they introduced an assignment statement. And I will use the squares of integers. You see this function call here. A function call in a functional language can be replaced by its implementation. So if I were to take this here and simply stick it there and put the values in, it would still be the same program. Let me show that to you. There we go. I have now taken that first call to print squares, and I've just put the values in. But of course, I have to do it again. But I've got to do it again. And I'm simply substituting the function calls for their implementations. If you think about this carefully, you'll realize that that turns in to the very silly implementation that I had put up there before with nothing but the 20 lines that printed the squares of integers. It turns into almost the same thing except for these cascading ifs. This was the model of computing that book that I recommended was using for all 249 of its first pages. You could simply replace a function call with its implementation. But when you introduce an assignment statement, that breaks. And this was the apology that they made in the book. Once you introduce assignment, you can no longer replace a function call with its implementation. And why? Because the state of the system may have changed. An assignment statement introduces the concept of time, which is why I show time here in such a warped way. Time becomes important whenever you have an assignment statement. An assignment statement separates the code above the assignment from the code below the assignment in time, because the state of the system has changed. In a functional program, that statement will always be true no matter what time it is. The value of f of x will remain the value of f of x no matter what the heck the time is. No external force can change the value of f of x. To put that into a j unit, or an n unit, for those of you who are crippled in that way. By the way, who's using n unit? Who's using that other thing? MS test. Stop doing that. It's slow, it's complicated. Use n unit. Or there's another one now, x unit, I think, written by the same guy who wrote n unit. So, anyway, look at that statement there. Should that statement pass? Should that test pass? If f is functional, that statement will always pass. But if f contains an assignment statement that somehow changes the state of the system, that function could fail. That statement could fail. Imagine staring at that in a test and noting the test failing. What conclusion would you have to come to? You'd have to come to the conclusion that f has a side effect. What's a side effect? A side effect is an assignment statement. All side effects are the result of assignment statements. If there are no assignment statements, there cannot be side effects. Only assignment statements change the state of variables. If there's no assignment, no variable can change its state, and so there cannot be side effects. When you have a function that gives you a side effect, you need another function to undo the side effect. Consider the function open. It opens a file. You need another function, close, to close the file, to undo the side effect. Consider the function malloc, the old C function malloc. That creates a side effect. It allocates memory. You need another function, free, to undo that side effect. If you seize a semaphore, there's another function to release it, to free it. If you grab a graphical context, there is another function to release it. Functions with side effects are like the Sith. Always two there are. And they are separated in time. The one must always come before the other, before in time. Malloc must always precede free, Open must always precede close. Close, we hope, follows open. What happens when you don't do this correctly? Leaks. One of the gross symptoms. Leaks. Has anybody ever had a memory leak? You were using assignment statements. You were using functions that had side effects, and so you had a memory leak. What have we done in our languages to protect us from memory leaks? Garbage collection, the greatest hack ever imposed upon any programmer. Garbage collection, the final admission that we are terrible at dealing with side effects. We've put it into our languages now that we're so bad at dealing with side effects, our languages have to clean up after us because we are incapable of cleaning up after ourselves. That's what side effects do. Unfortunately, we don't have garbage collection for semaphores. We don't have garbage collection for files left open. Maybe some of us do. Many of us don't. We don't have garbage collection for all of the funny functions out there that have side effects. So we still have the problem. We've only introduced this horrible hack of garbage collection in the one case where we can get some control over it. So let me show you an implementation of the bowling game. How many of you bowl? 10-pin bowling, you know, well, you don't need to know how to score bowling. It doesn't matter. I'm just going to show you these two implementations, and we'll look at them. One of them is sort of functional, and one of them is definitely not functional. And we'll look at the functional one first. This is functional, sort of. It's functional if you blur your eyes enough. We begin with a function called roll. This roll function allows us to capture the number of pins knocked down by a ball. You would call this function every time you rolled a ball at the pins, and you would record into a list the pins that you knocked down. Now you think, well, this is some kind of state change. Not exactly. Each element of this list is being initialized. No value of the list is being changed. There's a variable here called current roll. That's definitely getting altered. However, that alteration only exists within the roll context. So once I have called roll for the entire game, I don't need to worry about that variable anymore. So this is not perfectly functional, but I can blur my eyes. I can step back from it from a few thousand feet and say, well, it's functional in the sense that once you're done calling roll, you don't care about this variable anymore. The list has been built. And then I can process the list. And I can process the list by walking through the list, looking at the balls, looking at the rolls, and deciding whether or not the rolls are a strike or a spare or a non-striker spare, and manipulating some kind of pointer. Once again, this is not perfectly functional because I've got this variable here that gets manipulated. However, once score returns, all these variables are destroyed. So from the point of view of the call to score and its return, there's no side effect. Internally, there are side effects, but that's a very limited scope. So at a very limited scope, this is not functional. At a wider scope, it is. Or I could do it this way. I've got this enum here. This is the stateful representation. I've got some enum here. It's going to record the state of the system as I roll balls. And here's the roll function. The roll function attempts to calculate the score in real time. And in order to do that, it's got to store a state variable. And that state variable alters the way this program works from roll to roll to roll to roll. So a call to roll will do something different depending on the state it was left in by the last call to roll. This one is not functional. This one is highly stateful. If I were to put the call to roll here, in the first example, it would pass. If I were to put the call to roll there in the second example, I doubt it would. If I were to put the call to score here, it would probably pass, but in the second one, well, it would pass too because it didn't do anything. Which of these two is simpler? That's the stateful version with the finite state machine in it. This is the functional, quasi-functional version. Which of those two is simpler? It turns out the functional version is much simpler. Which one is faster? Probably the stateful one is faster. Probably. Because it's doing less work. It's saving state, but it doesn't have to squirrel away all those variables. I'm not sure. I haven't measured them. Probably not a huge difference. Which one is more thread safe? The functional one is much more thread safe. There's hardly any variables to get confused in there, but the non-functional one has that state variable. And if you had multiple threads calling roll, it would get pretty interesting. Which one uses more memory? The functional one does. It's got to save all those rolls up in a list before it can process them all. And that's one of the issues. What do we know about memory? It's cheap. How cheap is memory? I got a thumb drive here. What is it? I don't know. Probably 5 gigabytes. No, it wouldn't be 5, would it? 8 gigabytes? Maybe 8, maybe 16. I really don't know. I don't use it. I just keep it in my pocket because it's fun to have 8 gigabytes in your pocket. 8 gigabytes in my pocket. How many bits is that? 64 billion bits in my pocket. How did that happen? Because memory didn't always used to be cheap. We've got lots of it. We have virtually infinite amounts of memory nowadays. This machine here has a 0.5 terabyte of solid-state memory. When's the last time you saw a rotating disk? Does anybody in the room still have a rotating disk in their laptop? Of course, all of you have laptops. Yeah, oh, there's some rotating disks over here. I'm so sorry. If I'd asked that question a year ago, about 10% of you would have put your hands up. If I'd asked that question 2 years ago, half of you would have put your hands up. If I'd asked that question 5 years ago, everybody would have had their hand up except for one person, and we would have all hated him. Memory has gotten cheap, absurdly cheap. We are filthy rich with this stuff. We are wealthy beyond belief because memory is pouring out of every orifice of our bodies. It's unbelievable how much memory we have, and it's dirt cheap. Hundreds of dollars for a terabyte. That's absurd. It didn't used to be that way. Who knows what that is? That's memory. Core memory. Core memory of the 1960s. Every one of those little donuts you see there is made out of iron. Every one of them had to be put into that network of wires by hand. There was no machine that could make core memory. It was woven on a loom by human beings, bit by bit by bit. It was frightfully expensive. I used to purchase this when I was a teenager I would get surplus, Army surplus core memory for $100, hundreds of dollars for 1,000 bits. I once purchased a solid state memory rack of 512 bits. It cost me $512. $64 billion worth of memory when I was a teenager. We used to do bizarre things like try and figure out how to store bits on rotating memory surfaces. This is an old disk. Look at that thing. It was 14 inches across. It had, I don't know, a dozen platters. You wrote bits on the top and on the bottom of each platter. So the heads would slide in there and they'd write on the top and they'd write on the bottom. The heads had to move in and out to find the different tracks on the disk. These things would spin at about 3,600 RPM. That's a drum. Look at how inefficient that is. Right? We would write on the surface of that drum. This is an old deck tape. We used to write on the surface of mylar tape impregnated with iron, magnetic tape. And that's an old CRT memory which used the persistence of the phosphors to remember bits. If a phosphor point was glowing and you hit it with the electron beam, it would impede the beam, and you could detect that with the amount of current you put into the beam. So you could tell if a point was still glowing. Absurd kinds of memory things. Nowadays, of course, it's dirt cheap. Functional programming was invented in 1957. Before OO, nobody even thought of OO. Before structured programming, Dijkstra had not yet written his paper about GoTo being considered harmful. And yet in 1957, we were already doing functional programming. Functional programming was the first of the three major paradigms to be invented, the last to be adopted, oddly. And why? Because memory was too expensive to make it practical. I mean, do you remember when we worried about that? In a date? But that's changed. We don't worry about memory anymore. Memory is too cheap to worry about. We throw it away in megabyte lots. We think of a megabyte as infinitesimally small. So why should we change how we program? Should we change how we program, given that memory is dirt cheap? Well, probably we should. Functional programs are simpler. You can prove this to yourself by writing a few. By the way, it takes much longer to write a line of functional code than it takes to write a line of non-functional code, but you wind up with far fewer lines of functional code, oddly enough. And the amount of time spent programming turns into a smaller amount of time because you don't have to worry about the state of a variable. So it makes them easier to write, although it doesn't feel that way, because every line you have to think about much harder. And yet, in the end, the functional program is easier to write. It's easier to maintain. Everybody says this about everything, right? It's always easier to maintain. But it actually is. And why? Because of that. There are no temporal couplings, no side effects, no worries about what function to call before any other function, or what function must be called after some other function. How many of you have debugged for weeks only to find that the problem was two functions that were called out of order? And you swapped the two, and the system started to work, and you don't know why these two functions had to be called in this order. They just do for some reason. This is not an uncommon debugging scenario. In a functional program, that disappears. I said here that there are fewer concurrency issues. In a purely functional program, there are no concurrency issues because there's no variables. What is it that makes a program unthread safe? Side effects. two functions trying to create a side effect. The two of them collide because of thread swapping, and they improperly modify the side effect. If there are no side effects, if there are no assignment statements, you can't have thread problems. Why did I say fewer? Because in most functional programs, there is a portion of the program, a well-isolated portion of the program, which actually does do some assignment. And in that portion, you can get some concurrency issues, but in the vast majority of the code, you don't. So we can get a lot less concurrency problems if we're using functional programs. Has anybody debugged a race condition for a month and then given up and said, well, just reboot the thing every once in a while? You never have to ask. Think about this, right? You're in the middle of a debugging session. You're sitting there, you've break-pointed your way deep down into the code, and then you ask yourself, what the hell is the state of the system? You never ask that. In a functional program, the system has no state. What you're looking at here is Moore's Law. From 1970 to 2010, the number of transistors in a chip has been going up at, notice this is a log scale. So at some doubling rate, which people usually say is about 18 months. So every 18 months, the number of transistors on a chip doubles. Here's the clock speed. That's this dark blue line. And look at what happened here. Right about 2003. It went flat. Do you remember 2003? We got up to 3 gigahertz clock rates. And the yields were bad. The power was bad. We dropped down to about 2.5 gigahertz, and it stayed there for 10 years. For the last 10 years, we've been sitting at 2.5 gigahertz, and it doesn't look like it's going to change. There's a possibility of some new materials that might make an incremental change in the clock rate, but not the geometric growth. This growth here is gone. We're not going to see that continue up here. It's folded over. But the number of transistors on the chip has not. The density has continued to grow. Now that's going to fall over too, probably pretty soon, because we're down to about 20 atoms in a wire. So there's only so much further you can go. But for the moment anyway, we continue to double this density number, and that has given the hardware engineers the ability to do more cores. How many of you have 4 cores in your laptops? How many of you have more than 4? Yeah, don't fall for the hyper-threading thing. You know, they'll tell you there's 8 cores on there. There's not 8 cores on there. There's 4. And they do this lie they call hyper-threading. Who's got true 8-core? Yeah, okay, good. I recently bought a 12-core machine for my daughter. Actually, that was 3 chips with 4 cores each. But they still share nicely. Notice what's happening here, right? We're multiplying cores. Why would we multiply cores? Because we want to keep increasing throughput at some rate like this. Cost per cycle, dollars per cycle. We want to increase this by this rate. But we can't do it with clock rate anymore, so we do it with cores. And the hardware engineers have started making some very bizarre trade-offs. Do you know all that caching stuff they used to put in the chips? The L1 cache and the L2 cache and the L3 cache and all that pipelining goop they used to do to squirrel away the instructions that were about to be executed, and they'd flush that if you did a jump. You know all that stuff? They're ripping all that stuff out. They're going to make the processors slower. They're just going to put more processors in. So as we add more and more cores, the individual cores will slow down, but the throughput of the chip goes up if you can take advantage of those cores. How do you take advantage of those cores? How do you do that? How good we are at writing threaded code? Now, multi-threaded code is code which operates one instruction at a time. The processor is still a linear processor. The operating system tells one process it can go, and the operating system is like a mother. It watches over the process as it runs. It makes sure the registers are loaded before it runs. When it tells it to stop, it grabs all the registers and squirrels them away and puts the process away in a nice place, and then gets the next process out and unpacks the registers and lets it run for a while, and it takes nice care of the process. There is no mother when you've got multiple cores running, because now you have simultaneous execution, not concurrent execution. You've got 4 cores, you got 4 instructions running simultaneously, and they're all hitting the bus, and they're all angry animals scrapping for that bus. They want that bus, they want their bytes. They say, give me a byte, here, take this byte, give me a byte, and there's no operating system to hold them off and make them behave nicely. So we, programmers who have grown up with the nice operating system that lets us use our threads nicely, and we still can't do that well, are now faced with the jungle of the bus. And how many cores will we have to deal with? We got 4 now in most of our chips. Some of the chips will have more. If I come back here in 2 years, your laptops will have 8. If I come back in 4 years, your laptops will have 16. If I come back in 10 years, your laptops may have 512 cores. How are you going to write programs? How are you going to write systems that behave well with 1024 cores? How are you going to get the maximum out of your machine when you've got 16 384 cores? How are you going to do that? And you may think, well, the operating system will handle that for me. I don't think so. I don't think so. I think the operating system folks are going to go, hey, programmers, this is your problem. So we, programmers, who have for the last 60 years lived in this fantasy world of one instruction at a time, are now facing the real world. And the real world is the world of competing cores on a single memory bus. And we're going to have to deal with that somehow. And maybe one of the ways to deal with that is to give up the assignment statement. Walk away from the assignment statement and never use it again except in very disciplined environments. Maybe all of us have gotten addicted to assignment, and we're going to have to break that addiction. If these 2 F's are executed on separate cores, doesn't matter, so long as there's no state change. So I can take my function, the same function, executed on multiple cores. So long as there's no state change, I'll get the same results. This is why these languages have suddenly become important. Anybody notice that these languages, 5 years ago you didn't hear much about a functional language? Why have these languages become suddenly important? And it's because of this multi-core problem. Everybody's trying to figure out how to solve the coming problem, the freight train that's on the tracks ready to run us all over. And out of this has come a number of languages. Some of them are old. These languages are very old. Erlang is becoming very popular now, functional language, but very interesting in the high reliability market. Right? It's possible to write very high reliability functions in Erlang because they've got a very good recovery mechanism, and it's a nice functional language. Who studied Erlang? This would be worthwhile. There's a couple of good books on Erlang. Just read the books, get an idea. Write a couple of lines of code, and you'll see what's going on in this language. There's another language derived from Erlang called Elixir, which makes Erlang look a little bit like Ruby. Who's a Ruby programmer here? Ooh, one guy. One guy. Wow. You guys are really convinced about .NET, aren't you? In the United States, a Ruby programmer can write a number on a piece of paper and find someone to pay him that number, because all the social networking companies are using Ruby on Rails, and they're all convinced that they've got to have good Ruby programmers, so the market for Ruby programmers is going through the roof. That's a bubble. It's going to pop. I don't know when it'll pop, but right now, if you're a Ruby programmer in the US, you feel pretty good. Who's doing a little F sharp? This is the .NET answer. Okay? A reasonably functional language. I'm not horribly familiar with it, but I've looked at it a little bit. Slightly hybrid, but you can do some functional code in it. Scala on the Java side, more of a hybrid language. What do I mean by a hybrid language? A hybrid language is a language that supports functional programming but allows you to do undisciplined assignment. And if the language allows you to do undisciplined assignment, you can't really call it a functional language. I put Clojure down here in a special font because, in a special color, because Clojure is a language which is functional. It's essentially Lisp. Who knows Lisp? All right, some of you do. How many of you are afraid of all those parentheses? Yeah. Okay, so here's the thing about the parentheses in Lisp. You know, a function call in Java looks like this, or in .NET, it looks like that. You've got this name of the function, open parenthesis, argument, close parenthesis. That's how you write a function call. In Lisp, what you do is you take that open parenthesis right there and you move it there, and now you know Lisp. That's it. There's no extra parentheses, same number of parentheses. It's just that funny little positional move, and it scares everybody to death. Right? And then the convention of the Lisp programmers is to stack all the closing parentheses at the end of the line instead of putting them on separate lines like .NET and Java programmers do. But if you count them up, same number, no difference. Right? That's the difference. Just move that parenthesis like so. I like Clojure because it runs on both the Java and the .NET stack. It sits on top of the CLR or the JVM. It's a very nice little Lispy language. There's some good conventions in it. It imposes strict discipline on assignment. It's possible to do assignment, but you cannot do an assignment in Clojure unless you, in effect, open a transaction. An assignment statement in Clojure is treated like a database operation. You have to open up something like a transaction that can retry, and then you can do your assignment. And it detects collisions in threading space, and it retries and makes sure that there's no threading problems. That's what a Clojure program looks like. It doesn't look that different from a Ruby program or a JavaScript program, except, of course, for that open parenthesis, which scares everybody to death. If you were to take that open parenthesis and just move it there, or maybe there, it would look a lot better from your point of view. But all I'm doing here is defining a function named AccelerateAll, which takes an argument named OS, and it calls the map function and maps the function accelerate to the list of objects. Pretty straightforward stuff. This gets people crazy here. That's a function call right there. It's the greater than or equal operator, and then the two arguments. And everybody wants to move that into the middle, and they can't quite manipulate it in their brains to move it in the middle. It takes a little practice. Hey, here's how you add. That's a function, the plus function. We don't have operators in these languages. We just have functions, but we can use special characters for the function names. So that's the plus function, adds those two. This is the divide function, takes that, divides it by that. Not real hard to figure out. What about OO? OO is procedure plus state, right? And state is evil in the functional world. So does that mean that when you are writing functional code, you can't be doing OO? And the answer to that is no. You can be doing OO in a functional program. You just can't manipulate state. Because remember that OO is exposed procedure, but hidden state. Remember, we were supposed to be hiding all of our state in an OO program. All the variables are supposed to be private. You're not supposed to know those variables exist. And so it's possible to write functional programs using an OO style, and not only are you hiding all the variables, you're also not changing any of them. All of the objects become immutable. Now, you may think to yourself, yeah, immutable. That means I got to make copies. Every time I change an object, I got to make a copy of that object because I can't modify the state of the object. And it turns out that these languages are actually very clever. The languages, the implementers of the languages understand that linked lists can have multiple heads. And you can make a linked list look like two different lists by moving the pointer to two different heads. So you can modify a linked list without making a copy, just by creating a different head. And they use this technique to make it possible to modify objects without needing to make a copy. The old object is still there, but it gets linked to the new version of the object by some very clever linked list manipulations, which keeps the speed very high. In Clojure, this is called persistent data structures. When you modify a data structure, you do not destroy the old version. You just keep a new version. That should sound familiar to you. That's your source code control system. You modify your source code, but you don't destroy the old version. And you have very clever ways inside your source code control system to make sure that you relink to the old source code if you want to. You can move back in time. And they don't make copies of all that old source code. What they do is they very cleverly store the differences in just the right way, and they maintain the pointers so that you can reconstruct the source code at any time. That's what these persistent data structures do. Remember that OO is a lot more than just state. OO is dependency management. OO is about managing the dependencies inside of an application so that high-level concepts are independent and low-level concepts depend on high-level concepts. This is called dependency inversion. And that dependency inversion can still be done in functional programming. In an OO program, we use polymorphism to do that. In a functional program, we can still use polymorphism. There's no reason that you can't have a function, and when you call that function, it dispatches to different other subfunctions based on some kind of type identifier. All of that can still be done. And Clojure as a language allows that to be done, as well as the others. Functional languages can still have polymorphic interfaces. They all still need dependency management. None of that stuff changes. They all still need the principles of object-oriented design and the principles of dependency management. But they need something else. They need the discipline imposed upon changes of state. So a language like Clojure has special functions in it, transactional memory, that allows you to change variables, but only in the context of a transaction. This discipline has to be maintained if you're doing a Clojure program. There's no locking. You don't block for anything. You just make sure you've got this nice transactional memory. Because locking requires superpowers. It's difficult to know when to lock and when not. Has anybody debugged an application horribly, only to find out that you forgot a lock somewhere? Locking requires superpowers. Let's not use them. Locking means that you have side effects, and you're trying to lock around those side effects. And with that, I think I'm going to... I had a lot more to talk about, but with 5 minutes left, I think I'll open it up for questions. Are there any? You're going to have to holler and put your hand up really high because I can't see anybody. Yeah.
Right, memory is cheaper, but what about cache misses?
Memory is cheaper, but what about cache misses? Right, so we do have the problem now that we've got all this caching in our processors, but the hardware guys are ripping all the caches out. All those caches are going to go away. All those hardware caches are going to go away. We still have software caches. And yes, the more memory we use in our lists and the more memory we use in our persistent data structures, the more we're likely to have some issues there. Functional programs can be a little slower. Not much. A little bit slower because there's this funny linked list structures that you have to be walking through. But the kind of time difference is fairly small. And if we're talking about multi-core, well, then the time difference is almost irrelevant. Because we're trying to find a way to program with 1024 cores. If that costs us 2% for each individual core, it's not much of a cost. Anybody else? Do I see a hand somewhere? It's hard for me to see. Okay, I don't see any hands. Oh, one guy.
How do you structure your program? Because now I have nice objects and I place functionality.
So the question is, how do you structure your program? Because now I have nice objects that I can put my functions into. How do I structure it now? And the answer is the same way. You still have data structures. You still have gatherings of data and functions that operate on that gatherings of data. The difference is that you don't change any of the variables inside those gatherings of data. In a good functional language, there is a way to create a suite of functions that operate on a particular kind of data structure. It looks like an OO language in that sense. Clojure has that facility, for example. You can create records, and inside those records you can put functions, and those records can behave polymorphically, just like methods in classes, except that none of the variables in the records can change. You have to create new objects, even though you're not actually creating new objects. It looks to you like you're creating new objects, and you can maintain state that way. All right, I think that's enough. Thank you all for your attention. I'll see you another time.